Emily, and welcome to Crash Course Chemistry. Today I'm going to be joined by some of my fellow scientists in training, Brinkley and Madelyn. And we are going to be exploring some of the weirdest substances on Earth. Liquids and solutions!
Liquids are weird for many reasons. For one, they don't have a designated shape. Liquids take on the shape of their container. Liquids are also super rare. Of all the elements on the periodic table, only 2 of the known elements are liquid at room temperature: bromine and mercury.
Most liquids we see in our everyday lives are actually solutions. A solution is a mixture of particles of a solute dissolved in a solvent. Here we have a cup of water, and here we have some salt. One second. When I pour some salt in the water, and I mix it, it dissolves. Because salt is an ionic compound and water is polar, the water molecules are able to dissolve the salt by pulling the ions apart. When the salt is dissolved in the water, the mixture is classified as a solution.
Although liquids and solutions look different on a molecular level, both are classified as liquids by their state of matter. Different states of matter are created by intermolecular forces, which are the forces between separate molecules that hold structures together. Liquids could not exist without intermolecular forces.
There are 3 main types of intermolecular forces that help elements remain in a liquid state. The first type is London dispersion forces. These forces are caused when electrons cluster together briefly, causing a brief negative or positive charge to be created. Although these forces are small, they are still very important because they are the only forces that allow nonpolar substances like neon to condense into a liquid.
The second type of intermolecular force is dipole-dipole forces. Dipole forces are created by attractions between the opposite partial charges in polar molecules. The dipole-dipole forces are very important to molecules as they increase attraction and lower potential energy, making substances more stable.
The third main type of intermolecular forces, hydrogen bonding, is similar to dipole-dipole forces as they both involve polar molecules. A hydrogen bond is the attraction between a hydrogen atom and an extremely electronegative atom. Hydrogen bonds are very important for dissolving solutes in solvents like water, since they allow the water molecules to bond with solute molecules that contain either nitrogen, oxygen, or fluorine.
It is the relative weakness of intermolecular forces that allows a substance to change into a solid, a liquid, or a gas. And it also decides which state an element will take at room temperature.
Liquids are very different than solids and gases, and they have their own properties as well. The attraction properties of liquids, also known as cohesion, create many of these properties. The cohesive properties of liquid make the free edges of liquids curve as much as possible to approach a spherical shape. This is seen when we overfill this bottle cap with water. While in the cap, the water forms a concave meniscus because the water is more attracted to itself than the cap. Water molecules will pile up, clinging to each other because of the strong intermolecular forces and surface tension holding them together.
In larger liquids like mercury, the molecules are more attracted to the glass than itself, so it forms a convex meniscus. In larger molecules like honey, with many hydrogen bonds, intermolecular forces are so great that the liquid develops a resistance to flow, called viscosity.
A substance's solubility, the amount of solute that will dissolve per volume of solvent, is affected by molecular structure, pressure, and temperature. And keep in mind that not every solvent can dissolve every solute. The structure of each molecule, specifically polarity, determines whether it will dissolve and how well it will dissolve. For a substance to dissolve, it needs to interact favorably with the solvent. And this only happens if they have similar polarities, which allow them to form in-solution structures, spacing the solute particles out evenly and allowing the solute to dissolve.
For most solutions involving solid solutes and liquid solvents, the solubility can be increased with an increase in temperature and pressure. If enough solute is dissolved in the solvent, the solution can become classified as a supersaturated solution. Supersaturation is a state of a solution that contains more of the dissolved material than could be dissolved by the solvent under normal circumstances. The hot ice experiment demonstrates the properties and phenomenon of supersaturation. For the hot ice experiment, you'll need a pan, 4 tablespoons of baking soda, 4 cups of white vinegar, a Pyrex measuring cup, and a pan. First, add the white baking vinegar to the pan. Then, add the baking soda slowly while waiting for it to fizzle. After the solution has settled, turn the stove on medium-high and let the solution rest for about 30 minutes. When the time is up, scrape off the white powdery crystals on the edge of the pan and set it aside. Refrigerate the solution for 30 minutes in a Pyrex measuring cup. Place the collected white crystals on the pan and slowly pour the solution over it to form hot ice.
In the hot ice demonstration, a supersaturated solution of sodium acetate and water is created because the solubility of sodium acetate increases substantially at higher temperatures. Precipitation requires the formation of a small solid crystallite in the solution, a process called nucleation. After the crystallite forms, a second process called growth enlarges the crystallites to the macroscopic level. Nucleation requires a rough surface, which is why we use the crystalline sodium acetate to form our ice. The precipitation of a solid from a solution results in a decrease in the disorder of the system.
The laws of thermodynamics state that for a process exhibiting a decrease in entropy to occur spontaneously, like the precipitation of a solid from a solution, the process must also liberate heat. Therefore, the introduction of a solid crystallite of sodium acetate will warm itself as the sodium acetate precipitates from the solution, thus giving us hot ice.
If you are paying attention to this episode, you have learned what makes solutions different, the 3 different types of molecular forces that create liquids, including London dispersion forces, dipole-dipole forces, and hydrogen bonding. You have also learned how the relative strength of intermolecular forces influences the properties like cohesion and viscosity. Finally, you learned about what makes solutions, what influences solubility, and how the experiment of hot ice demonstrates a phenomenon of supersaturation.